presentation. So I appreciate the committee's efforts in bringing this together. I think this will be an interesting discussion. Hopefully this will generate future discussions as well. So Mary, I'll turn it over to you.
Thank you very much. For those of you who don't know, Keith is retiring, so we're going to be without his wise counsel going forward. And we thank you very much for stepping in and chairing our council and on all of your guidance over the past year. It's been a good ride for everybody. So best wishes in the future. With no further ado, we have some very esteemed panelists here with us today. I'm not going to spend your time doing an introduction of all of them. They're going to introduce themselves as they speak, and they know that they've already decided the order they're going to speak within. We'll start with Chip Fletcher, please. Chip.
Hello, happy midday to all of you. I want to put a link to an opinion piece I published last week in The Hill for everybody in the chat, and it's not happening. I'll get to that a little bit later. My name is Chip Fletcher. I am Associate Dean for Academic Affairs at the School of Ocean and Earth Science and Technology at UH Manoa. And along with a group of absolutely brilliant graduate students and technicians over the last couple of decades, we've spent our time learning how beaches operate and attempting to both model and more deeply understand how they are going to respond to sea level rise in the context of community assets, especially. So allow me to get started here. I will share my screen and get us going. The title of today's symposium is Climate Change, Sea Level Rise, Shoreline Protection, and Erosion Prevention. And I want to spend a few minutes at the end of my talk talking about these terms in red: shoreline protection and erosion prevention. These are standard terms in government and in dealing with the problems of shoreline change. And I want to point out how they lead us into they lead us down a path of thinking that is actually not in keeping with protecting the public trust. But let's begin with what we know about global warming. This is the record of annual average temperature relative to the mean temperature between 1880 and 1900. This data set is from NASA, and 2020 came in last year, tying 2016 as the warmest year on record, and the two of them are just a few tenths of a degree short of 1.3 degrees Celsius warmer than the pre-industrial period. Now, 1.3 C is a useful benchmark to keep in mind because all of the nations of the world have pledged through the United Nations Framework Convention on Climate Change to stop global warming at 2 degrees C and to make extraordinary efforts to stop it at 1.5 degrees C. And a report came out in 2018 from the Intergovernmental Panel on Climate Change called the 1.5 report, which illustrates what the world will be like when global average temperature is 1.5 degrees Celsius above the pre-industrial average. And that report was filled with lots of information that indicated it would be a very unsafe world, both for natural ecosystems as well as for human communities. And since that report the effort at the United Nations and indeed among all the world's nations has been to cut greenhouse gas emissions in order to stop global warming at 1.5 degrees C. And as you can see here, we are very, very close to reaching that temperature. In fact, many projections have us reaching 1.5 degrees C and then rising above it by the end of this decade. The 6 warmest years in this 150-year record are all the past 6 years, and the 10 warmest years are all in the past 2 decades. Since 1970, you can see this blue dashed line. This is a linear trend that global warming has been following at about 0.18 degrees Celsius warming per decade. However, in the past 6 years, as you can see in the red circle, average annual temperature has now departed from this trend. And this indicates that the rate of global warming is accelerating. I want to begin with a few statements. One is that sea level has risen 8 inches since the 19th century. And look at the background photo. Only 8 inches of sea level rise, and we see very dramatic impacts on our communities. And this is Sunset Beach about a year ago at the end of summer, I believe it was, August, September timeframe. Everything we know about future sea level rise tells us that it will be many feet higher, rising much faster, and is essentially unstoppable for centuries. Though if we cut our greenhouse gas emissions and we manage to stabilize global warming, sea level rise can also be slowed and limited. And I'll show you why it's essentially unstoppable on a human time frame in a second. And this quote from Michael Oppenheimer, who was the lead author of the last IPCC report, which was in 2019, focusing on sea level rise. There is no scenario that stops sea level rise this century. We've got to deal with this indefinitely. So here, in an image that speaks 1,000 words, is what global warming looks like. This is temperature change relative to the global average. And you can see that the oceans are cooler than the global average. And for centuries, in fact, the models indicate that for millennia, the oceans will be absorbing heat from the air and thermally expanding as they attempt to get into equilibrium with that warmer air. That's why sea level rise is essentially unstoppable, because they're already out of equilibrium with the air temperature. And through vertical circulation in the ocean, those warm air temperatures, which translate into warm surface waters, then need to translate into warm bottom waters. And many of those lower layers are many centuries old. So it will take many centuries, in fact, over 1,000 years before the full temperature of the ocean represents the full temperature of the atmosphere. And we continue to dump greenhouse gas into the atmosphere, and we continue to drive global warming, which is accelerating. So this process of equilibrating the ocean to the air has not really had a chance to act in a serious manner. What you can see from this image is that continents are warming much faster than oceans. And this puts bread baskets, our main food production centers, and communities at risk, because those are all located on these rapidly warming continents. And most of the continental land mass is in the Northern Hemisphere. And it's in the Northern Hemisphere summers that climate scientists pay very close attention to heat waves, especially with regard to our bread baskets. Because the continents are warming so quickly is one reason I am happy to be located in the middle of the Pacific Ocean. I think that oceanic islands are one place to be where you can avoid the very worst in terms of the heat waves. Notice also that the Arctic is warming much faster than the global average. In fact, it's warming between 2 and 3 times faster than the global average. This is because it's losing sea ice, exposing dark ocean, Arctic Ocean surface, which absorbs sunlight, releases heat. And so the Arctic is warming very quickly. It is the planet's refrigeration system. The sea ice in the Arctic Ocean reflects sunlight. And as we lose that bright surface, the ability to cool the entire planet is also being lost. Greenland is in the Arctic, and as it experiences melting from Arctic amplification, it is forming a layer of volcanic ash and wildfire ash that is not being swept away by meltwater. It's accumulating as a lag deposit, making the Greenland ice sheet darker and darker. And in fact, the breakdown of these ashes provides nutrients for bacteria to grow on the ice, which themselves are dark. And so Greenland is experiencing less and less reflection, more and more absorption of sunlight, which is accelerating its melting. All that meltwater streaming off of Greenland makes the North Atlantic today the coldest it has been since it was first measured by Ben Franklin, sailing back and forth between Europe and New England. And that cold water has slowed an important circulation system called the conveyor belt, which pulls heat out of the Indian Ocean, out of the Southern Atlantic, and up into the North Atlantic, and normally distributes that heat across Europe, keeping the Northern European nations much warmer than they would be otherwise. But this global conveyor belt circulation has slowed as much as 15%. And so there's less warm water going through the South Atlantic. That means there's less evaporation off of that warm water, and we are seeing drought hit the Amazon and Congo rainforests. We also are leaving heat, warm water in the Southern Ocean near Antarctica, and you can see these red areas. That means that this warm water in the Southern Ocean is leading to accelerated melting in the Antarctic. And in fact, that warm water, significant parts of it are down around 500 meters depth, and they are causing the melting of floating ice shelves from underneath, which we'll look at in just a minute. Greenland melting has quadrupled since 2010. Meltwater coming off of Greenland represents about 1/4 of global mean sea level rise. And recent research says that the Greenland ice sheet, ice discharge into the ocean is far surpassing snow accumulation, and that the whole ice sheet is in a constant state of loss. Even if climate change stopped, the ice sheet would continue to lose mass, because the high elevation plateau of the Greenland ice sheet is lowering. And as it lowers in elevation, the probability of melting increases and the probability of snowfall decreases. The ice on Antarctica melt has tripled since 2010. It currently represents about 14% of global mean sea level rise, especially from this very dark area called the West Antarctic. There are a series of glaciers that flow out into the ocean, and they are buffered by these floating ice shelves. But warm water, as I mentioned, is being trapped underneath these ice shelves and is melting them from below, as well as warm air in the southern summertime is melting them from above. And the ratio of that melting is about half and half, 50% and 50%. These floating ice shelves are grounded, and landward of this grounding line where they are stuck on the bottom, the continent actually slopes back. And so once the floating ice shelves are freed from grounding, there's nothing to prevent all the upstream ice from flowing rapidly into the Southern Ocean. And two glaciers in particular, the Pine Island Glacier indicated by P and the Thwaites Glacier indicated by the T here, are flowing very rapidly, and they're showing new damage areas, especially if you look at P2 here, you can see these tensional fractures. As the ice pulls away from the bedrock walls that contain it, this is new deterioration of the ice that's being seen for the first time. In fact, a paper came out just last week. This is the Pine Island Glacier. It's color-coded for speed, and the movement of ice in 2009 was about 4 kilometers per year into the ocean, and it's now about 5 kilometers per year. And the author of this paper describes the Pine Island ice shelf as ripping itself apart. Again, it's these ice shelves that are buffering or preventing the continental ice from flowing catastrophically into the ocean. We have ice in the world's mountain systems as well, and all of these alpine glacier systems are losing mass. They are all melting, and combine all the mountain ice in the world, and it is showing a very strong retreat. It's losing 280 billion tons per year. That's actually equivalent to how much ice is being lost off of Greenland. So ice loss and thermal expansion of the ocean as it gets warmer are the two primary drivers of sea level rise. And you can see that the heat content of the ocean here is measured back as far as 1960, is rising and accelerating. And in fact, 2020 set a global record for ocean heat content. Thermal expansion of the ocean represents about 1/3 of sea level rise. And when you add these together, our physical models project that this century, we may see as much as 3 to 4 feet of sea level rise. That is if we do not get rapid West Antarctic ice sheet discharge into the ocean. If we do see ice shelf deterioration and Pine Island or Thwaites glaciers rapidly flow into the ocean, we could be open to multi-meter sea level rise late this century, on the order of 6 feet or above. That potential is very real, and the research is suggesting that the probability grows as we learn more and more. Projections also tell us that 2 centuries out, we're looking at on the order of 10 to 16 feet of sea level rise, again, if there is not catastrophic ice decay. Are we going to be successful at stopping global warming? Well, there's great news from the renewable energy sector. Renewable energy use is accelerating. You can see this histogram at the bottom from 2011 up to projected 2021 and 2022. Renewable energy additions to the global power production sector are growing. Renewable energy generation last year, despite the recession, grew by 45%. That's the fastest rate in 2 decades. 280 gigawatts were added to the world supply, which is equivalent to all of Germany's power needs. China accounted for 80% of new solar and onshore wind installations. And the projections for this year and next year are that renewable energy will account for 90% of new global power capacity. This momentum is likely to continue as long as lithium continues to be available. Nickel, cobalt, lithium, copper, rare earth metals, these are an important question. Do we continue to have access to these important minerals? The world, however, is on course to use ever more energy. And the current surge of renewables, while it is some cause for hope, it's really only a modest one. Carbon emissions are set to soar this year. the International Energy Agency projects global economic output this year to rebound more than 2% higher than 2019 levels. Demand for all forms of fossil fuels are set to grow. Coal demand is projected to increase by 60%. This is more than all renewables combined, just the coal demand. Emissions are projected to increase about 5% over this year. This reverses the 80% drop, or this reverses 80% of the drop in emissions last year in 2020. By the end of this year, the IEA projects that greenhouse gas emissions end up only 1.2% below 2019 emissions levels. And next year, there could be an even stronger rise as air travel returns. Emerging economies are driving the energy demand back above 2019 levels. Global energy-related CO2 emissions are heading for their second largest annual increase ever. And 940 million people still do not have access to electricity. They desperately need energy, and fossil fuels are often the only sources available to them. They deserve to have a higher quality of life. They deserve to have easy access to energy. This is one reason why I think it's critically important for the developed nations to strongly assist the developing world. We do this not only to help them, but to help ourselves. Recovery from the COVID recession has put the oil industry back in business. In the first quarter of 2021, Shell reported a profit, a $2 billion profit. Exxon posted a profit. BP posted a profit of 3.3 billion. Chevron. So the slowing of the oil industry was temporary, and they are coming back full bore. Now, let me end with some words about the natural world. Averaged between 2010 and 2019, 86% of our anthropogenic CO2 emissions came from combustion, and about 14% came from land use in the form of deforestation and agriculture processes which turn soil into a source of CO2 to the air. Of these sources, 46% go into the atmosphere and cause global warming. 31% are absorbed by photosynthesis, which we'll call the continental biome or the terrestrial biome. So a third of our CO2 emissions, and it's CO2 that's responsible for about 70% of anthropogenic global warming. So that's why we track CO2. Roughly 1/3 is taken up by photosynthesis on land, and the remaining 23% is absorbed into the ocean and causes ocean acidification. So this 1/3 of photosynthesis is a critical partner. Unfortunately, it looks like we are approaching a tipping point for photosynthesis. So plants use photosynthesis to remove CO2 from the air, but they also engage in what's known as respiration that releases CO2 to the air. Photosynthesis has a thermal maximum. Past that, photosynthesis sharply declines while respiration continues. Carbon uptake by land plants is already degrading. With continued emissions and continued global warming, carbon uptake is degraded, and it's projected to be reduced by 50% as early as 2040. This aspect of the natural world's losing its capacity to store carbon for us is not accounted for in any of our national policies, and it's not accounted for in the United Nations pledges to cut our emissions. An example of this is the Amazon basin. The Amazon contains more than half of all tropical rainforest. It lost 1/3 of its biomass last decade because of deforestation, drought, tree mortality, farming. And during last decade, the Amazon released 18 billion tons of carbon dioxide and absorbed only 15 billion tons of carbon dioxide. So we now feel that the Amazon is no longer a sink of carbon, it is actually a source of carbon dioxide. There's 6 emission sectors where we need to cut our greenhouse gas emissions. Electricity in general is responsible for 25% of emissions. Food, agriculture, various types of land use is responsible for 24%. Industrial processes, about 1/5. Transportation, roughly 14%. Buildings, 6%. And then other types of emissions, fugitive emissions and flaring, about 10%. And there are multiple pathways to take in each one of these sectors, depending on the specifics of the economy. Basically,
Chip, this is incredible.
I'm just about done, I promise.
Thank you.
This is our history of carbon dioxide emissions from 1850. And this is what we need to do with our carbon dioxide emissions by 2050. We need to reach zero emissions by 2050. And every single pathway for doing this that has been published requires negative emissions. That is, that we pull CO2 out of the air. And we have done absolutely nothing on the global stage, and also really nothing here on the local stage with regard to that, that sector of global warming solutions, sequestration. We have another 15 years if we target 2 degrees Celsius. Lastly, because sea level rise is inevitable for many generations, this idea of shoreline protection suggests that we need to stop erosion. We also have erosion prevention. If you stop erosion, you are going to kill beaches. We actually need to change our concepts here and allow erosion to happen. Because as you can see, many of our shorelines have sand deposits on the landward side of the shoreline that will be released by erosion and will allow a beach to migrate landward as sea level rises. Sea level rise is not the automatic death knell of a beach. Beaches can survive sea level rise, but we need to learn to get out of the way. And that is something that we still have a lot of work to do. Thank you very much, and I'm sorry I went over time.
That's quite all right, Chip. We could listen to you all day. I've got these other 4 panelists that I asked, we want to speak, and I'll let them get even with you. With that, Sam.
Mary, in the spirit of time, why don't we pass this on to the other speakers and then come back at the end and pick me up if we still have time.
Okay.
Yeah.
Okay.
Thank you.
So that means that we will have Bethany share her mana'o at this time. Bethany Morrison from Hawaii County.
Hey guys, okay, Sam, now I owe you one because I can't follow Chip's presentation very well. So let me share my screen and get started talking about what Hawaii County is trying to do to address these issues. Let's see. Okay, so, Chip outlined that we are up against some really serious issues. And so I just want to review Hawaii County and kind of the ways that we're thinking about trying to address some of this. We're a pretty unique island. We have a very diverse coastline. We have some beaches, but mostly rugged lava formations and steep cliffs. But overall, the size of our island, as you can tell, presents some challenges for us to try and manage some adaptation strategies for sea level rise and erosion of the shoreline. There was a report that came out for the state that looked at sea level rise vulnerability, and for the island of Hawaii, we only have passive flooding models available, but from that, we were able to understand some of the impacts that we can expect. And we've also seen through king tides, which really demonstrate for us what the potential sea level rise would look like on a day-to-day basis. And so we're able to actually see that sea level rise in action through those king tide events. And then the Big Island also is sinking because of the weight of our volcano. And so that just adds to the impacts of sea level rise. We also have seen some significant storm events. We had Tropical Storm Isel, which produced some serious wave run-up and caused quite a bit of damage. I think they had 25-foot storm surges through that event. Hurricane Lane produced 52 inches of rain for some of our communities, and that caused several landslides around our Hamakua coast that have been chronic, but when they have the high rain events, they can, produce these large slides. So that's just some of the impacts that we're seeing from climate change, and more importantly, what are we trying to do to address these? So we're really focusing on the integrated approach to dealing with these. I'm a long-range planner, and so I'm really focusing on how do we get climate change to be part of all of our planning efforts. And so we have been supporting and partnering with local nonprofits who are doing great work on sea level rise studies. We have initiated a look at our shoreline and riparian setbacks. We are working to integrate our climate action planning efforts with both mitigation and adaptation strategies. We're in the process of updating our comprehensive general plan. And we also recently updated our multi-hazard mitigation plan. And both of those, general plan and the hazard mitigation plan, really focus on climate change for the first time. So a little bit more specific on what we're doing to address sea level rise. We are working as part of a nationwide cohort currently with ICLE. And again, we're working to integrate adaptation and mitigation into one planning effort. So this is a collaborative effort with our research and development and our planning department office. I'm working on the climate change adaptation planning piece. And this is just a little identification of our scope that we're working towards. Really, this came about through some recent conversations about how do we deal with these specific issues impacting our county assets. And so you can see the photo here that's really attempting to show us what one beach park might look like with pretty minimal sea level rise overlay. And so the conversation is really about, what adaptation strategies do we apply to these county assets? And just to give an example, this one, we had a grant that did the coastal hazard assessment to show the sea level rise